Hello guys, let's solve this GFGPO today. Uh, Largest square form in a matrix. Given a binary matrix of size n into m, find out the maximum length of side of a square submatrix with all ones. Um, okay, so let's understand the question and find out the logic, guys. Basically, what he's saying is, um, suppose there's a matrix, it contains zeros and ones. You have to find a square which has the largest side length, right? You have to find a square which have the largest side length. So um, let's solve this one, guys. It's not that hard. It's a medium question. We can solve this one. Okay. So for this one, I'll use tabulation, guys. If you means you can see the video. If you see the view, I think you can understand it, guys. I'll explain it clearly. You have to know recursion means I will use for loops actually, but if you know recursion, it will be very easy for you. You can use memoization also. Basically, it's a DB question, but I will maximum. I'm using tabulation here. It's a easy process, so I will explain from scratch, guys. So let's start. So we have to find out the square in it, right? So first, the basic point is suppose if it's a zero here, take an index. Let's take an index. If it's a zero here, can we form a square with it? No, right? So no square here. If anywhere it's a zero, then we cannot form a square with it, right? But if there is a one here, suppose here it's a one. So at least one square will be there. That square is this one, right? Side length one. At least one square is there. If there is a one, at least one is there. But more than or one, we have to check. We have to see. So what I'll do is, if it's zero, no problem. No, we cannot form any square with it. But if it's one, we have to check, right? So what I'll do is, I'll write a table here. I'll write a table here. What does this table do? First question, what does this table do? I'll tell you guys. One, two, three, four, and five. Right? So same here. One, two, three, four. So five, six here. So what I'm telling is, suppose this is zero. Don't check this one. Suppose let's take any two indices. Suppose 4 and 3, 4 comma 3. If we take 4 comma 3, now what will happen? This index, right? This index. Okay. Uh, what I am telling here is I'll construct a table. Suppose this table is DP. Means this table name is DP. Not anything complicated. Just this table name is DP. And this have I and J. Means I plus 1 and J plus 1. Same here. Same I plus 1 and j plus 1. Same I plus 1 and j plus 1 means n plus 1 and n plus 1 means. Same here 5 means here 6 will come. Here 4 means here 5 will come. That's it. Nothing different. Same table here. And I will initialize with 0 initially. I will use vectors and initially there will be zeros everywhere. Now what I am doing is, what does this ij signify? Suppose TP ij. What does this signify? Now I'll tell you guys. What does this signify is, ith index is 4. Let us consider ith index is 4 and the ith index is 3. Now, from here to here means till this index, the maximum means including this index means we have to include this index and till this index, maximum square, right? Suppose here one is there, including this index. The what is the maximum square side length? 3. So dp of 5 comma 4 is 3. Are you getting my point? That's the same thing. dp of ij means till including this index, means including this one, the maximum side length of a square. If we include this index, this will come and this will come. Means this is the edge, right? We will not include this and this. Okay. So including this is the significance of dp of ij. Now how are you building the table? No, I think you got it right. So now what is the answer here? If we know the dpij, means if you know the table here, the answer will be maximum element of dp of ij, right? Right? Maximum element of dp of ij. Answer is maximum element of dp of ij, right? So how are we filling the dp of ij table, this table? Now let's write a relation, guys. Let's write a relation here. Suppose let me take, suppose this table is there. 1 1 here. Normal 2D table. Now the DP table for it means this is the normal table. Normal means just normal table like this matrix. This is a matrix here. Now this is a DP table. DP table means what? Till this, I told you right, till this index, the maximum square possible, including this index. So suppose this index is there. Till this index, maximum what? 1, right? One element, one square, 1. Till this index, what? 1. Till this index, 1. But till this index means 1 is there, at least 1 should come here, right? If 1 is there means, suppose there are here zeros also, here 1 should come. But after 1, what will come here? Right? So this one means this value depends on these three elements, right? Right? This value means what I am saying is this value depends on these three elements, right? So this value is equal to at least 1 will come here. It is 1 is there. If 0 is there, no problem. But here 1 is there. So 1 plus minimum of these three, right? Minimum of matrix of I minus 1 j and I minus 1 j minus 1 and I j minus 1. Minimum of these three, right? Are you getting my point? 1 means at least this is there. We are including this. But 1 plus minimum of I minus 1 j minus 1 means what? Why? How can I tell this is? See, suppose this is there. This element is there. Till here, what is the maximum square formed? 1, right? Till here, maximum square form 1. Till here, maximum square form 1. If these three are there, now see, suppose here 1 is there. This is the maximum square form. But if these three are possible, then if this is also there, then we can add. So see, how can I say? Now the big table is there here. Some big table is there. These three elements are there. This is the actual table. This is the element we have to find, right? This is actually clumsy. Let me explain it here. Suppose this table is there. These three tables are something we don't know. These table values depend on these three, right? How they are dependent? Suppose this table maximum value, including this one, is a square, will be here. This table, including here. This table, including this element, will be here. This one value, 1 will be there. Actually, 1 will be there. Plus minimum of these three, right? If 0 is there, if anywhere here 0 is there, it will come obviously 1. 1 plus minimum of 0 means it will absolutely become 0. But there can be any value, right? See, this is the recursion relation, guys. This is the obvious recursion relation. Suppose this element is there, this element is there, this element is there. Suppose here anything can be there. Here, if it's 0, then minimum will be 0. But here it's 1 is there. If 1 is there, here also if 1 is there, here also if 1 is there. What I am saying is, here it's 1. If here it's 1, it is 1, it is 1. What he is saying, there is a DP table including this element with 1. And this also is 1. This also here is 1. So obviously 1, 1, 1 is there. If we add another one, there should be another, we can form another square, right? So 1 plus minimum of these three. DP means how, why, you can ask how are you saying minimum value? How I am saying minimum value means there can be cases, right? Like suppose this forms, suppose here 2 is there, here 3 is there. Suppose let me erase this one again. I'll tell you again. This is a table. If 2 is there, here 3 is there. If 2 is there, 2 means what? It can form two squares. Means 2 squares means actually 2. Here 3 means it can form 3. Means 3 means 3 side length square. Here 2 is there means 2 length square is there. 2 length square means at least it will cover these two, right? This is a square. So this will be the square. 3 means it will cover 3. 2 means it will cover the 2. If you see carefully, this can be a square, right? Means how can I say? Here 2 means this is a square. Here 3 means this will be a square. Here 2 means this will be a square. Now intersecting these three, what will be the answer? This one, right? How this came? Means at least these three elements are ones, these three are fun, these three are fun. We are intersecting these three. Means we are minimalizing, right? Intersecting means minimum of one, minimum of these three elements, these three tables. How these three are formed? These three are formed from above the values, right? See, this is formed from these three. This will be formed from these three. This will be formed from these three, right? So everything is recursive, guys. Everything is recursive. So I'm thinking that you're understanding my point. You're understanding my point. So the basic recursive relation is this, guys. 1 plus minimum of matrix I minus 1 j, I minus 1 j minus 1, I j minus 1. So let's go ahead, guys. This is the recursive. If you didn't understand it, think it again. Basically, what we are doing is we are filling the table values from here, right? We are filling the table values from here. These table values we are filling from here. Initially, everything is 0, but we are filling the table values carefully. How we are filling? Initially, everything is 0. See, that's why I took one base indexing, guys. If suppose if here 0 is there, if I take one base indexing here, what will happen? 1, 2, 3, 4, 5, 6 here will come, right? That's why I took 1, 0, 1, 2, 3, 4, 5, 6. Are you getting my point? Now here 0, 1, 2, 3, 4, 5. Exclude remaining, okay? Exclude remaining, okay? So let me exclude remaining and erase this off, okay? Now this is the DP table, right? Now this is the DB table till here, till here. Let me mark here. Let me mark here, okay? Till the black line, okay? Till here. This is the DB table, right? So what we can say, 0 means, suppose I am taking here 0 based indexing, so 1 based indexing. So 0 means, suppose here 1 means matrix here hot 0. If here I take 1, then here will be 0. But if I take 0, nothing is there, right? DP of minus 1 will come. DP of matrix of minus 1 will come. Matrix of minus 1 not there, right? So first row is 0, right? If 0 is there, okay. If 0 is not there, if less than 0 is there, nothing, right? I'm taking that's why 1 base indexing. Here I'm telling you matrix DP of ij means till matrix, DP of ij means till index matrix of I minus 1, comma j minus 1. Are you getting my point? Means if ij I told, then matrix of I minus 1 and j minus 1 will come. I minus 1, j minus 1 means this one. Like suppose 4 and 3 is there. Now DP will be what? 5 comma 4. Why I am taking this? Because at least we need at least one column to fill first. By that we can recurse the relation here. So 0 means nothing is there. 1 means matrix of 0 will come. But 0 means nothing is there, right? So first row will be 0. From here we write the recursive relation easily. Okay. So let's go it out, guys. Array. Sorry, guys. I'll go it out. So here DP. So I'm writing a table here. This is a DB table, just a DB table. Okay. Why I'm taking this? I can take an array also, but if we take vector, it's more convenient to initialize Zoola values. Okay. So let me check here. Yeah. Okay. Um, so everything is initialized to 0. Okay. J less than equal to m, j plus plus. So now DP, initializing DP. If matrix of ij, see, if it is 0, if matrix, sorry, I minus 1, I told you, right, 1 base indexing. Okay. If I minus 1, j minus means 1 base indexing actually means if I take n here, matrix of ij I wrote means nth index will not be there, right? N minus 1 index will be there. Okay. If it is not 0, it can be there. But if it is 0, no value, right? So dp of I j equal to 1 plus minimum, right? Minimum of dp of I minus 1. Okay. Let me use these braces. I minus 1 j minus 1 j minus 1 and next I j minus 1, right? Now what I will do, answer. I'll define an answer here. I'll okay. Initially here answer is not there, so I'll write answer here. Okay. Now okay. I'll write an answer. Okay. So I hope it works fine. I think it should work fine. It's okay. So submit. I think it should work fine. Yes, guys, it's working fine. Actually, I done it 3 times actually. So that's for today, guys. I'll post another video on. I can optimize this to small extent. I'll post another video on this, guys. Thank you, guys, for watching.